You know all those smart devices we have everywhere? What actually gives them their spark? Well, today we're going to pull back the curtain and look at the tiny brains that run pretty much everything, microcontrollers.
I mean, it really does seem like magic, doesn't it? This one little chip takes a command and poof, something happens in the real world. So how on earth does it do that? That's the big question, and that's exactly what we're going to break down right now.
Okay, so what is a microcontroller? You'll often hear it called an MCU, and really it's just a mini computer packed onto a single chip. But here's the key difference. Unlike your laptop that can do a million things, an MCU is a total specialist. It's built to do one specific job, and it does that one job over and over and over again with insane reliability.
Now, you might be thinking, hang on, isn't that just a microprocessor? And that is a great question. It's a super common point of confusion. A microprocessor, that's just the CPU. It's only the brain. Think of it like a car engine, super powerful, right? But it's totally useless without a chassis, wheels, a transmission, the rest of the car. A microcontroller, on the other hand, is the whole package. It's more like a smart pocket watch. It's got the brain, the memory, the ways to interact with the world, all of it right there on one single self-contained chip.
So what's actually inside this all-in-one wonder chip? Let's metaphorically crack it open and see what really makes it tick. And you know what? It's probably a lot simpler than you'd think.
All right, so pretty much every microcontroller has these four key parts. First up, you've got the CPU. That's the brain, the part that does all the thinking and follows instructions. Then you've got memory, which is kind of like its notebook for jotting things down. Next, and this is super important, you have the input-output ports, or I/O for short. These are its senses, its arms, its legs. It's how it interacts with the world, from sensing a button press to actually lighting up an LED. And finally, you have peripherals. These are like specialized tools in its tool belt, things like timers to help it keep perfect time for specific tasks.
And this is how it's all even possible. It's just mind-blowing when you think about it. See, at the most basic level, all of these components, the CPU, the memory, everything, are built from billions of teeny-tiny electronic switches called transistors. And I love this analogy from branch education. Think of a single transistor like one of those little studs on a Lego brick. By itself, it doesn't do a whole lot, right? But when you start connecting them together in really clever ways, they form what are called logic gates. And those are like the actual Lego bricks. And once you have enough bricks, well, you can build anything, even the brain of a computer.
Okay, so we've got this tiny brain, all packed onto a chip. But how does it actually, talk to the real world? That's where those I/O ports we mentioned come into play. They're the critical bridge between the chip's digital world of ones and zeros and our physical world of buttons, sensors, and lights.
The key player here has a name you'll hear all the time, GPIO. It stands for General Purpose Input Output. And that general purpose part is the real secret sauce. It's what makes these things so powerful. It means that each one of those little physical pins sticking out of the chip can be programmed by us, by the developer, to be either an input to listen to the world or an output to do something in the world. That flexibility is it's everything.
Let's make this super concrete. Let's walk through a really simple example. Imagine you press a button and you want an LED to turn on. Okay, so step one, you press the button. That sends a low voltage signal to one of the GPIO pins that we've set up as an input. Step two, the MCU's brain is constantly checking that pin and it reads that low signal. Step three, the code we wrote kicks in. It basically says, hey, if that pin is low, then you need to do something. So, step four, the code tells a different pin, one we've set as an output, to send a high voltage signal. And finally, step five, that high signal travels out of the pin, powers the LED, and boom, it lights up. See? It's just a simple loop. Read, process, and then write. That's the core of it all. Of course, a microcontroller on its own is, well, it's just a fancy piece of silicon. It's only as smart as the code we give it. It has no idea what to do until we tell it, step by agonizing step. So the big question is, how do we get our brilliant ideas out of our heads and into the chip?
It's basically a four-step recipe. First, we write the code. A programmer sits down at a PC and writes out the instructions in a language that's pretty human-readable, something like C++ or Python. Second, we compile it. A special piece of software called a compiler takes our code and translates it into the only language the MCU understands, binary, just raw ones and zeros. Third, we have to program the chip. We use a little piece of hardware, also called a programmer, confusingly, to physically transfer that binary code from our computer onto the microcontroller's memory. And finally, the fun part. You give it power, the MCU wakes up, and it just starts running that code. Presto, your idea comes to life.
Okay, so now you know the secret. The so-called magic happening inside all of our everyday electronics, it's not magic at all, is it? It's just a tiny, well-programmed microcontroller faithfully doing its one specific job over and over and over again.
And I mean it when I say they are everywhere. Think about it. Inside your washing machine, there's an MCU reading your button presses and perfectly controlling the water valves and the motor. In your car, oh, there are dozens of them, managing everything from your dashboard display to the critical timing of the engine. They're the brains inside robots, constantly reading sensor data. They're what keeps drones so perfectly stable in the air. They are literally the heart of countless medical devices, industrial machines, you name it.
So, if there's one thing you take away from this, let it be this. No matter how ridiculously complex a device seems, the microcontroller at its heart is always doing the same simple thing. It reads inputs, it processes those inputs based on the code it was given, and it controls outputs. Read, process, control. That is the fundamental loop that runs our modern world.
It's not an exaggeration to say these tiny brains have totally changed our world. They're just hiding in plain sight, powering literally everything we rely on. And what's so cool is that they've made what used to be incredibly complex control systems accessible and affordable for pretty much everyone. So, now that you've seen behind the curtain, now that you know the secret behind the magic, the only question left is, what are you going to build?